In this video, we're going to continue our conversation about Java collections and generic classes. So we continue with the set of topics related to search algorithms. So sometimes we need to be able to execute a search on a long list of items. So long list of items could be a Java array or Java collection that contains a sequence of objects. So the length of the list, of course, may impact the speed of the search that we are trying to execute, and also the presence or absence of an item that we are searching for can also impact the length of the search or the time required to execute the search. So generally speaking, we have a collection of items, just a sequence of items on the list, and our search item happens to be at the end of the list. It will take a lot of comparisons to find it. If search item is not on the list, then we will compare the entire collection elements set and still consume a lot of time in order to complete the search, even though the search will come back as negative results, not finding an item. So sequential search is therefore not efficient for large lists. In fact, it can be proved that on average the number of comparisons made by sequential search is equal to the half of the size of the list. So we call it linear complexity of the search. So basically the length of the search will be proportional to the length or the size of the container where we're searching for our item. So in order to be able to search more efficiently, the collection can be sorted. So there's an example of a selection sort algorithm where the list is sorted by selecting list element and moving it to the proper position. So essentially we select an element and move it to the proper position by reordering the elements inside the collection. The algorithm finds position of smallest element and moves it to the top of unsorted portion of the list, and then repeats the process until the entire list is sorted. So this search algorithm can be viewed like this. It's called selection sort. So an example here demonstrates that we have a list of integers. Okay, it can be placed inside a basic Java array, or it can be placed somewhere in the array list, but we have a list of integers. And you can observe that these values are unsorted. They appear to be in some sort of random order, perhaps in the order in which they were entered into this list. So the first step in selection sort algorithm is to locate the smallest value. So, of course, to be able to verify that a specific value is the smallest value, we have to scan the entire list of our values and find that, for instance, number 5 is the smallest. Step number 2, we swap it with the top of the list, because we say, okay, if we want to reorder this list in descending order, of course, the smallest list has to stay on top. So, for the lack of better choice, we just stick the top element at the position where the smallest position was found. So this reduces the unsorted, remaining unsorted portion of the list by one element. So now the unsorted list becomes one less the size of our original list size. So then we continue to do the same steps. We take a look at the unsorted portion of the list, we iterate through all of the elements, we find the smallest element, and again we swap with the next element. So now 2 of these are sorted and the unsorted list remains. So we continue this set of iterations. We'll be able to locate 16 to be the smallest one and swap it with 24, and then eventually swap 24 with 30 and so forth. And so basically we will finally sort everything through the entire collection, through the entire list of the elements. And this is the selection sort. And this is an actual example of a selection sort, where basically we specify some sort of array as an example, which we call list, and we specify the length of this list, and we start executing this algorithm. And so basically there are two of the loops. One is the main loop that goes through all of the list elements, and the inner loop finds the index of the smallest number, and the bottom portion of this algorithm is to swap the top element with the smallest one. So this is an example of selection sort, and of course sorting is a very popular algorithm with collections of items. So selection sort complexity can be determined as, for instance, if the list has length n, then the selection sort makes exactly this many, so the length of the list multiplied by the length minus 1 divided by 2. And comparisons are exactly this many comparisons that we make. This is just a calculation of the complexity of this sort. So if we have a list of 1000 integers, and we want to sort the list, selection sort will make 500,000 comparisons, and then it will do the swapping, and that swapping will amount to 3,000 assignment statements that we have to execute during this sort. So it's an expensive operation, but sorting is a required task. So that's what it takes to do it when we use the selection sort. Another example of a sort is called insertion sort.